All right, another bizarre capacitor question, right? Of course, everybody does this, right? Okay, we always, oh, whoops, ignore that. It's like the Wizard of Oz. Don't even look at that. All right, this is 23 millifarads, right? So the capacitance is 23 times 10 to the minus third farads, right? That's milli. Not microfarads, but millifarads, which is quite large, right? Yeah. And then 46 volts is this voltage there, right? I'm trying to look at the. I'm hoping that when I printed this, that it didn't. I don't know. We'll see. All right. So let's see. A battery of electric circuit is shown used to investigate the temperature change in a wire that is wrapped around a mercury in glass thermometer. Right? We just call them thermometers, but in the UK, right? It's a mercury in glass. I shouldn't be putting those on tests. They're dangerous. All right. A battery of EMF, that's just the voltage, 46 volts, and of negligible internal resistance, which we don't know about yet, okay, is connected to a capacitor and to a coil of resistance wire using an arrangement of two switches. So basically, they charge up the capacitor to this voltage, right, and then they discharge it through this resistor like that, right, okay. And by the way, this question from the mock test is exactly like the test question. I don't think there's any difference. All right, so how do you find the energy? Energy in a capacitor is it 1/2 CV squared, where that's the voltage, right? Resistance, you're going to use this guy. V is V naught, e to the minus t over RC, right? That's really just tau. Right, tau is RC, and that's how the formula has it, but there it is, right? And R is 15 ohms. C is 23 times 10 to the minus third farads, right? Or 0.0023 farads, right? Okay, let's see. I assume it's complete. So basically they're asking the time. The initial voltage is 46. The final voltage is 1, is what they're saying. So they're just saying, it's completely discharged, because of course it never fully discharges, ever. It's an asymptote, right? All right. The mass of the resistance wire is 0.910 grams, right? So that is, by the way, 0.910 times 10 to the minus third kilograms, which is what we use for our formulas, right? Okay. And the observed temperature rises 89 kelvins, which is the same as 89 degrees Celsius. Estimate the specific heat capacity, right? So you're going to take this energy from A, this guy. That's going to be Q, and that's going to be MC delta T, right? And you have the mass. You've got the delta T. You've got the energy from A. The answer from A, right? And now we can figure out C, okay? And then include an appropriate unit for your answer. Notice how I wrote these, right? It's weird. It's joules per kilogram per degree Celsius, right? They think that that's the correct way to write the unit. So when they ask for the unit, be sure to write it in that weird IB way. Anything that's divided by, you say to the minus 1, okay? That's important. Or you won't get that second mark. It's sad. Even if you say joules per kilogram per, right? They don't think that's correct. All right. So just one energy loss in the experiment. I'll let you come up with that, right? There's got to be some way that all of the energy from that capacitor doesn't go into the wire, right? Okay. And the effect that it will have on the value of the specific heat capacity of the wire. So ultimately, right, this specific heat capacity is going to be the energy that you got in A divided by the mass of the wire divided by the change in temperature. Okay? Now think about this. Okay? If we lost heat to the surroundings or something like that, right? Okay, or some of the energy didn't go into just the wire, maybe it has to heat the thermometer too or something like that, right? Okay? If we lose some energy to that, this calculation stays the same because we just assume that energy is what the wire absorbed, right? The mass is, we massed it. That's not going to change, right? But if we lose energy, we're going to lose, the change in temperature will be smaller than it should be, right? If that's smaller, something happens to this, right? So just look at the math of that. In other words, losing energy makes this delta T smaller than it should be, right? So that's going to do something to the specific heat, all right? Make that argument. And then let's see, is there any other thing that's on the test? Oh, yeah. Yeah. There is a question that's not on the mock test. I'm sorry. I added this question. And the question is, draw a graph of the discharge of the capacitor through one time constant. Think about what it does through one time constant. You need to get the shape of the curve right. You got to get the amount of drop correct. Okay? Think about what it does for one time constant. All right? And then, spoiler alert, on the test, there is an extra credit opportunity to show that you can solve a cathode ray tube problem, just like is on the FA 17.2. Okay? Good enough. Happy hunting.